Okay, so last time I was talking about these robust uncertainty principles, which were kind of what are they are called, either we can call robust or stable versions of the other uncertainty principles I gave. Here, especially for the support, is what we are saying. So one of them that we proved was this: if suppose you have a function on your group and it has a 1 delta approximate support. A is a 1 delta approximate support, and F hat has a set B, which is a 1 epsilon approximate support. So approximate support means we say it's a P delta approximate support if the LP norm on that set is at least 1 minus delta proportion of the LP norm of the function itself. Okay, so that means if delta is small, it puts most of the mass, most of its weight as measured by the LP norm on this set. So if A and B are not supports, that is the difference from the earlier situation, that they are not support, but they are 1 delta support and 1 epsilon support. So they can be much smaller than the support. So then you still have a inequality like the size of A times size of B is at least 10 times 1 minus epsilon into 1 minus delta. So we saw this one last time. So I will not go over that. But as I said, the more stronger one is the one that Donoghue and Stark proved, that this is also true for 2 delta and 2 epsilon approximate supports. Okay. So if F is from G to C and F hat is, and A is a 2 delta approximate support, B is a 2 epsilon approximate support, then the cardinality of A times cardinality of B is at least 10 into 1 minus epsilon minus delta the whole squared. Okay. So, and I had given an exercise, there's a 1 delta and 2 epsilon. So here it's a mixed one where the function you have a 1 delta approximate support, and for the Fourier transform we have a 2 epsilon support. This one is not too bad. You can do it like here. But let's prove this theorem. Before that, are there any questions? So let me prove. So for this, so it is a little more involved than the other uncertainty principles that we proved. For example, this 1 approximate supports was straightforward. It was more or less like the other one. Here it's a little more involved. Let's do this. So we introduce some operators. See, so what are these operators? So it's just convenient to write in terms of those. So let PA be restriction of F to A. In other words, PAF is F times indicator A. We just restrict F to A and put it equal to 0 elsewhere. PB hat is so here A is of course a subset of G and B is a subset of G hat. PB hat is the restriction of F hat to B. What that means is it still acts on F, by the way. So I go write like this. PB hat F is you take the Fourier transform, restrict it to B, and then take the check. Okay, so you go to the Fourier transform, then restrict it and come back. That's what it is. So you can also write it as the function whose Fourier transform is the restriction of the Fourier transform to B. That's another way to write it. So these are operators from L2 of G to, so these are projection operators on L2 of G to L2 of G. So why I introduced them? So the condition of so if you see the condition of approximate support. So what did we say? A is a 2 delta approximate support means it's the same as PAF. So this is the, of course, everything here is the 2 norm is greater than equal to 1 minus delta L2 norm of F. And similarly, B is a 2 epsilon approximate support means PB hat F L2 norm is greater than equal to 1 minus epsilon times right. I mean, because what we said is F hat. Okay, so this is because F hat indicator B has at least 1 minus epsilon times the L2 norm of F hat. Now use Plancherel on both sides. So basically that was saying that this function on here has 1 minus epsilon times the L2 norm of this of F hat. So take Fourier transform and use Plancherel. So you can write PB hat F has 1 minus epsilon times this. So what comes out of this is if you look at PB hat, compose the two. We can write a lower bound for that. What lower bound can I write for that? So we can write this as PB hat F 2 minus so I just wrote PAF as F minus, so I got PAF as F minus I minus PAF. So first part will be PBF, then this is 1 second. PAF is F minus identity minus PAF. So F cancels, PAF remains. So PBF is the first term. Second one is sorry, PB hat. Everywhere it is hat. PB hat PF minus PB hat of I minus PAF. Now this is greater than equal to PB hat F is greater than equal to 1 minus epsilon L2 norm of F. Now this being a projection operator, PB hat of anything, PB hat cannot increase the norm. Both PA and PB hat cannot increase the norm. It's clear, right? It can only decrease the norm. So this is at least I minus PA L2 norm of F, which is we know I minus PA, which is it is yeah I minus PA F will be
less than delta, right? Delta norm.
Yeah, that is less than. So it's going in the right direction, right? So is it correct? 1 minus epsilon minus delta.
Yeah, correct.
This is 1 I minus PAF L2 norm is less than delta times norm F2. So negative greater than equal to, right? Okay. So it is this. So PB hat PAF preserves almost the norm of F according to this. If F is like this. So what we will do is we will analyze the operator norm of PB hat PA. Okay. So in particular, so this one is fine. but we will now analyze okay, so any T operator norm, you may remember operator norm is, so T is some vector space to another vector space, okay, with norm V and norm U. Okay, so it's between two normed vector spaces. Then the operator norm is defined as the supremum of TV. This norm is taken in U divided by norm V, which is taken in V over V not equal to 0. Okay, that's how it's in phi. So which is same as one can also write supremum over norm V 1 of. Okay, so this is the operator norm. So yes.
So in this line where we have the LT norm of PB hat PAF equals something on the right hand side, yes, so that's also an inequality, right? Because we have used norms.
Oh yeah, you're right. Already triangle inequality has been used there. Yeah, that's correct. That is an inequality. Thanks.
Thank you.
That's an inequality. So this is an inequality. See, what this is telling is that for this function we have found one function such that this is more than this. That means operator norm is at least 1 minus epsilon minus delta here, right? So we will now get an upper bound for the operator norm. So by matching the two, we get a conclusion. Okay, so this is giving a lower bound for the operator norm, and we'll get an upper bound for the operator norm. Now, how do I get an upper bound for the operator norm? So there are many inequalities for operator norms. We'll compare it with what is called. So there is another norm. I might as well state it here. So let's take so now let's say I have an operator from V to V. Maybe it is also fine for two other vector spaces, but let me take the case of V to V to not get myself confused whether T star T or T star and stuff like that. So let's V a finite dimensional norm space. So what is the operator norm really? See, if T was a symmetric matrix, suppose if T was a Hermitian operator, that is, then what is the operator norm? What do you say? Yes. Anyone? Okay, so let's see if T was a Hermitian operator. So anyway, let's come to, I'll come to that. So it's related to the eigenvalue. See, the largest eigenvalue is what comes up. So anyway, so is that
so it is the largest eigenvalue, right?
Largest absolute value of eigenvalues. Yeah.
Right.
Because so maybe I do that first. Suppose if T was T star equal to T, then we can write T as lambda k vk star. Let's say these are the eigenvalues, these are the eigenvectors, and then for any v norm TV square will be you apply T to V, what you get? You get summation lambda k right? So this is an orthonormal basis. Vk eigenvectors form an orthonormal basis, and this is eigenvalues. So Tv is lambda k Vk in a V inner product Vk. So norm squared will give you lambda k V inner product Vk squared. Now, obviously, this is less than equal to the maximum of. Let's take if V is norm V to be 1. So this will be less than equal to max of mod lambda k. If you pull that out, what you are left with is summation V inner product Vk squared, that is 1. Which is 1. So the operator norm is actually less than equal to the maximum absolute value of eigenvalues. And you can see you can achieve that by just taking V to be V1 itself. If I take V to be V1, then that one, I mean, let's say lambda 1 is the one with the maximum absolute value. Then you take V to be V1, so you get 1 for that and 0 for the rest. So operator norm is seen to be, in this case, max of the eigenvalues. Now our T is not Hermitian, but it's related. So in general, what is the relationship? So in general, so if I have TV, so if you take TV, in general means I'm not assuming T is Hermitian. Okay. So then can I write something in terms of eigenvalues, eigenvectors? Yes, because this is TV inner product TV, which is T star TV inner product V. Okay. And so norm TV square is less than equal to norm T star TV into norm V. Okay. And we have seen T star T is a Hermitian operator, right? And it's also positive semi-definite. T star T, not only is it Hermitian, but it has non-negative eigenvalues. So we can write this as less than equal to maximum of lambda k. So these are eigenvalues of T star T times norm V, one norm V and another norm V. So we get norm V squared. So this is this times norm V, and so we get this. So we get that. So the conclusion is that norm T is bounded by maximum eigenvalue of. This is not equality. This is less than equal to maximum eigenvalue mod lambda k over k less than equal to n, where these are eigenvalues of. Sorry, so I should put square root now. If I put the norm, square root of this. Which one can, I mean, this is not that easy to get a handle on. So often one uses this inequality. It is less than equal to sum of the, since all this, so here actually as I wrote, no need to add absolute value because everything is positive. Okay, I mean non-negative. So let's write maximum lambda k. It's bounded by maximum sum of the lambda. Maximum is bounded by the sum. Since everything is non-negative, and that is actually the trace of T star T. Okay, trace of T star T is the sum of the eigenvalues of T star T. But that if you have the matrix, you can also get it as sum of the diagonal entries and so on, easier to handle rather than the maximum lambda k. Is okay? Any questions here? So this I was just saying some basic things about operator norm. So I defined the operator norm, and I have shown that operator norm is bounded by this one, this is also a well-known quantity. This is called the Frobenius norm or the Hilbert-Schmidt norm. So F for Frobenius. This HS is for Hilbert-Schmidt. It is, if you think of T as a matrix, what is this actually? So T star T, if you do trace of T star T, what you get is, you take this T as a matrix and put all the columns together as one long vector. Okay, and then take the Euclidean norm of that vector. So if you have an n by n matrix, you will get an n square by 1 vector. This is the norm of the Euclidean norm of that vector. That's the sum of squares of all the entries, square root of that. That's what it is. So we will be using this inequality. So this operator norm itself is harder, but we'll bound it using the Hilbert-Schmidt norm. Any questions so far? Okay, if not, let me come back here. So what we have done on this side is we have shown PB hat PAF is at least 1 minus epsilon minus delta norm F. Now we want to get an upper bound for this. We say that this is bounded by the Frobenius norm. Okay, Frobenius norm, which we will actually find exactly. So we will find that this is actually exactly. So this is a claim. This will be size of A times size of B divided by n square root of that. So we will show this. Okay, so once we prove this claim, assuming this, we are done. We see that this one is at least, because the operator norm is at least this, is at least 1 minus epsilon minus delta. So in other words, the product of the cardinality is at least n times 1 minus epsilon minus delta whole square. Okay, so that's what I wanted to prove. The product of these approximate supports is at least n times 1 minus epsilon minus delta the whole square. Okay, so the only thing that remains is to prove this claim that the Frobenius norm is actually exactly, this is an exact equality, so is equal to this one, size of A into size of B by n. So let's prove that. So what we will do is just find the matrix of this in a basis and then take the sum of squares. That's all we need to do. Okay, so just 1 second. Yeah. Oops. Where did I go? So let's use the basis. So PB hat PA is an operator from L2 of G to itself. So let's choose a basis. The most obvious basis, delta 1, delta 2, delta n. Okay, so, well, okay, delta, I mean the delta x's. Okay, so, okay, maybe I should write so we'll calculate the trace using this basis. because the operator, I mean, the Frobenius norm is just the trace, right? I mean, square root of the trace of that. So we want the trace of this. So the Frobenius norm of this let's square it so that I don't keep writing square roots. Trace of PB hat PA. Okay, T star T. So what does that make it? It becomes PB hat PA star, which is PA star PB hat, and then PB hat PA. Now, these are projections, right? So you don't need to worry about star is same as PA and PB hat square. So this is actually same as trace of PB hat PA. So projection means PB hat square is PB hat. That's part of projection. Also, PA star is same as PA, and PB hat square is same. PA square is also PA. You can remove the star and put PA in this side because it's trace. You can cyclically permute. So it's just PB hat PA, nothing more. Okay, so we don't need that long expression. So what we are wanting to do is, so this trace we will calculate in this particular basis. So it will be PB hat PA delta K inner product delta K. So, okay, so what is the K comma K entry of this matrix? That is what is the question. Now, what is PA delta K? I mean, PA delta K of any, let's call it J, is what? It is 1 if K belongs to A and 0 if K does not belong to, sorry, no, 1 second. What am I saying? Sorry, PA, what it does is restrict to A, right? So PA delta K of J will be, oh, sorry, PA delta K is anyway, yeah, okay. So what is it I want? PA delta K, and then I want to take PB hat of that. So PA delta K right. So what does delta K when restricted to A do? PA delta K is actually just either projection of delta K to A. I mean, restriction will be either it will be the delta K if K belongs to A and 0 if K does not belong to A. So that is clear. Right, because you are going to multiply delta K by indicator of A, and if K is not in A, that will be 0. Okay, now we have to take the PB hat of this. What does this mean? And inner product with delta K means the yeah, so 1 second, so I'm getting confused. So yeah, so we want to take this. This is, what does this do? You take PA delta K, PB hat PA delta K will be so we take PA delta K hat indicator B and then check. Okay, just let me check what I have written in my notes because it may be Right. Yeah, it is this. So P right. Okay. So PA delta K is anyway 0 if K is not in A, and if K is in A, then it is delta K hat, and then delta K hat indicator B check if K is in A. Okay, so maybe it is yeah. So I don't know if I'm conveying much here. It's a calculation. You just have to do it in this basis, and you get the answer. So delta K hat indicator B check, and then we have to take inner product with delta K. So this quantity turns out to be K equals 1 to N that inner product with delta K. So what it means is that is that function evaluated at delta K. So that is delta K indicator B hat at K equals 1 up to N. And what is the, sorry, so that check at K. And what is the meaning of this check? Yes. Okay, sorry, I'm getting confused myself. Let me just see my notes. Is it okay so far? I mean, this one, I mean, okay. So what is this hat at this check at K? I mean, so this check at K is, so what I have written in my notes is that this is the, maybe I'll get confused if I write both. So let's just try to figure out here. So delta K hat indicator B check at K. So what is check? I mean, check means, check is the by definition sum over chi in G hat delta K hat indicator B of chi into chi of K. By square root of N, right? So this is the definition of check. Now what is delta K indicator B, delta K hat indicator B of chi? Let's do that. Delta K hat indicator B. So that means, but sorry, so I made one mistake. Here I should not have taken K in 1 to N. It is actually only over K in A. That's a mistake. So here it is actually, yeah. See, I just get over K in A because otherwise this is 0. Now, so now we have to do this sum over, this is for a fixed K, and now we do sum over K in A, right? So what is, right, so what is that? Delta K hat indicator B of chi, and then yeah, what is that quantity actually? So that is actually delta K hat indicator B of chi is delta K So that means chi has to be in B, right? So, okay. So that is right. So this means chi has to be in B. This is the sum over K in A, chi in B. Otherwise, this quantity will be 0. And I have a 1 by root n here. Delta K hat indicator B of chi into chi of K. Now, what is this quantity? Is it just, what is delta K hat of? So now I don't need to write indicator B also. It is just delta K hat of chi. Oh, okay. That is, oh, I see. Yeah. Okay. Delta K hat of chi is just chi of K bar, right? You just use the formula 1 by root n delta K of chi, delta K of J, chi of J bar. So that will give you just chi of K bar by square root of n. So you just get chi of, so this is actually 1 by n sum over K in A, sum over chi in B, this one, chi of K bar, chi of K. That is 1. So this is gives you exactly cardinality A into cardinality B divided by n. Okay, so that was the claim. So if I confused, I can explain if people want to know. Basically, I wanted to calculate the Frobenius norm of PB hat PA, and I took the basis delta of delta functions, the standard coordinate vectors, and I did all the manipulations to get that. Okay, I'll be happy to explain it. Maybe it's easier to.
Sir,
yeah.
so is that a delta J of K or delta J of chi?
This is delta K hat.
No, not there. There in the definition here. Yeah, there below, a little below, and where you prove that that delta that would be chi K bar by root n there in the summation. Summation here.
So what I wrote was the definition of Fourier transform.
Yeah.
So let me write it. I wrote it shabbily. So delta K hat of chi. It is delta K hat of chi. So by definition, this is 1 by square root n delta K of J. Yeah, you're right. I think I had written something nonsensical. Chi of J bar. Right. This is what we should write. And that is actually only J equal to K will remain, and that will give me this. Is this what you asked?
Yes, sir. You wrote delta K of chi.
Yeah. That does not make sense. Yeah, it is delta K of J. That's correct. That's right. Any other questions, comments? So this is the Donohue-Stark robust version of the uncertainty principle, that even for 2 delta and 2 epsilon supports, you have this inequality. Okay. So they remark that although this is the way, actually the whole thing comes from here. So if you see here what happened in the proof. In the proof, we showed that PB hat PAF is more than or equal to 1 minus epsilon minus delta L2 norm of F. And so you get, on the other hand, so you have this. So this is the quantity we use to upper bound the operator norm. So as Donohue and Stark remark, if instead of this, suppose instead of this, I had any bound smaller than 1 for this, that would also give a conclusion, right? So that would also, if I had any small number than this, then that would give a conclusion about this. So they write some quantitative uncertainty principle. So let me just, I have written it as exercise in the notes. So if you take, so one of them is that, okay, I will leave it in the notes. So there are some quantitative things. So the key point is the operator norm of PB hat PA. We bounded it by this. But any bound more less than 1 will be giving you some conclusion. So there is some quantitative statements they make. So let me just mention what it is. So if you have G is supported on A, yeah. So they write some. This is an exercise in the. If cardinality A into cardinality B is less than equal to alpha n, alpha is less than 1, and some G is supported on A, then G hat, the amount that it can put inside B, is less than equal to alpha times the L2 norm. So in other words, if you have an inequality like this, that cardinality A, cardinality B is less than, I mean, this is using this, less than alpha n, then if G is supported on A, it cannot put too much mass on B, meaning not arbitrarily close to 1. So that sort of conclusion is a quantitative one. Yeah. Okay. So now I want to go on to some applications of these things. So, but are there any questions of this on this? So after doing applications of this, I will go on to the next topic. So, but there are some nice applications, so I will continue with that next time also. Now I will just start it, I think. So applications to signal recovery. So there are these signal recovery problems. So which are so the way one thinks of is here is like this. So we work with G equals Zn. Okay. So for it is more convenient if let's take n is 2m plus 1. It doesn't matter for application wise, and write this as not 0 to n but minus m. So the reason is the following. So then you have the characters, right? The characters are chi sub k of j, which is e to the 2 pi I kj by n. So why, I mean, so writing like this, so this is, I mean, so this is often done in continuous setting, but here also you can have the interpretation that when k is small, when k is 1, k is 0, it's a constant function, right? When k is 1, it is varying. When k is 2, it varies faster, it oscillates faster. So this is, k is like the frequency. So higher k, faster oscillation. So in other words, you go from j to j plus 1 and see how much change is there. That change really is e to the 2 pi I k by n, right? E to the 2 pi I k by n minus 1, that's the factor. And that is, so we can interpret it as high frequency. If I write it as 0 to n minus 1, then the high frequencies are near 0, but on both sides. So n is also low frequency. That's why I just wrote it like this. Okay, so that's all. So anyway, so here is a, so I was saying that for Poisson summation, I didn't have an application. Here is a simple one. So suppose yeah, so let me just 1 second. So yeah, what is the Poisson summation formula we proved? Yeah, so I have to, yeah, if n is so here the Poisson summation formula. You remember f from Zn to C, then n is written as PQ, then you sum f over multiples of P divided by square root Q is same as f hat over multiples of Q divided by square root of P. Okay. Multiples of P, right? JP. Okay, I'll move between this 0 to n minus 1 and minus m to m. It doesn't matter. So this we know. This is the Poisson summation formula. So because of that, so suppose okay, let's make one more this one. So you can just shift this function, shift the function. Okay. So suppose I want the Fourier transform to be, I want g hat of k to be f hat of k plus d, suppose. Then what will be the function g? So if I want g hat of k to be f hat shifted, so I'll write with the shifted one here, that's all. So that's why. So I want to write here 1 by square root p minus 1 kq plus d equal to it will be what? What will be here? That's the question. So if I want g hat of k to be f hat of k plus d, what does that mean? So what will be the function g? G is actually, yeah, what is the g hat of k? It is, this is g inner product chi k. I want that to be equal to f inner product chi k plus d. Okay, but that is chi k plus d is chi k into chi d. So I can put f times chi d bar here. Chi k. So g is actually chi g of, not g of sorry, chi d bar, chi d of k conjugate. So if I take this function g of k, which is f of k times chi d of k bar, it will shift all the Fourier coefficients by d. Okay, so what I get is, if I apply the Poisson summation formula to that, I get chi d of k conjugate. Okay, is that okay? I have just applied this to, oh sorry. So this is, I have to sum this over multiples of j, p. F of is this okay? I have here p minus 1. So it's just the Poisson summation applied to this new function f of k times chi d of k bar. On the left side, I'll get f of jp chi d of jp conjugate summed over j equals 0 to q minus 1 by root q. And here on the right side, 1 by root p, the Fourier transform will be shifted f hat of kq plus d. Okay, that's all it is. So because of that, so now suppose f hat is supported on what should I write? Minus, actually I'm going to confuse myself. So minus r plus 1 up to 0 and up to r.
Sir,
Yeah.
is that f hat of kq plus d or kq plus dq?
No, it is just shifted, right?
No, the rightmost in the Poisson summation. Yeah, is there a dq there as in is in?
No, this is the Fourier transform at kq, right? So this is g hat of kq. So what I want to here is g hat of kq. And here I want g of jp. This is g of jp, this is g hat of jq. Isn't that right?
Yeah. Thanks.
So now suppose f hat is supported on low frequencies. That is what we mean here. Minus r to r, where that is related to. So how much is this? So this is going from 0 to q. I think I take 2r plus 1 less than q or something like that. Less than or less than equal to. I don't care too much about that. So suppose I do this. So the meaning of this is f hat is not using very high frequencies. It is using somewhat low frequencies where this 2r plus 1 is less than q. So then what is the 2r plus 1 less than q going to make? Then if you look at this one, only one term appears there, right? Only one term will appear on that right side because nothing else, because this is going in multiples of q. So one of them will be in here and the rest will be outside because this whole length is less than q. So there is only one. So what we get is, so in other words, we get f hat of d is square root p by square root q times sum over j equals 0 to q minus 1 f of jp chi d of jp conjugate. Okay, so this is true for mod d less than equal to r. I can do it for all d in minus r to r, and I can write then the only term that remains here is the one with k equal to 0. If d is in minus r to r, then the term here that falls in this interval because f hat is 0 outside of this. Okay, so only one that comes is when k equal to 0, which is f hat of d. Okay, so what is the conclusion of this? So it's a very funny one. It means that you can recover. So what this shows is that can recover f hat. See, f hat is only supported on these points. So if I get f hat of d for d between this and this, I can recover. But that also means, and hence f. If you recover f hat, you can recover f from f sampled at multiples of p. So this whole interval is there. So 0 to n minus 1, you are sampling it only at multiples of p. But you can still recover the full signal. But of course, there is no magic in the sense of you have a restriction on f hat being supported on this. So obviously, dimension-wise, this is correct because f hat supported on this means the dimension of such space of functions is 2r plus 1. So, and which is less than q, and here you have q many quantities, f of 0, f of p, f of 2p, etc. So it's not surprising you can recover, but you can recover. So this is the what is called Shannon-Nyquist sampling theorem.
It's 1 o'clock.
Okay, it's already 1. I should stop now. Actually, we were told to stop 5 minutes earlier. I forgot. Yeah, so I will stop here. Then we will continue. So this is saying that you can, if you know something, if your function is band limited, that means in frequency domain it is supported on this shorter interval, then you can recover the function in this way from knowing its values at equispaced. So if you only see the signal at equispaced points with sufficiently high frequency, then you can recover the signal. That's what this is. Okay, I will stop here.